that would be 5%, right? So how?
If you think you have the answer, always check with me.
Okay.
Mistakes can raise and make mistakes. P is the cure rate and we're testing 0.65, right? We think it's probably better, so P would be greater than 0.65. State the rejection rule. Rejected test is really K, right? That's really all you need, right? Or S is the number of cured and the new treatment. And then I actually give you a sample here. Let's do where she go around. All right. 35 were cured out of 50, right? So is 35 big enough? I'm going to find p-value, right? 35 or more. You could use the continuity fraction, you'll get a better approximation here. And then you just need to standardize it. The mean is going to be n times p, right? And the standard deviation will be the square root of n times p times q. And then you just standardize it as we have been, and it's going to be 0.74, so the p-value is 0.2291. Certainly you would fail to reject it to 5%. The lowest level you can reject that is 23%. There's an indication, but it's not very nice. It's 'This is a paper.
And say we're talking about income tax. They're right.
Lansing does. Lansing has an income tax.
Yeah, well, actually, city has fun. Well, last. But it's like. Okay, so estimate proportion would be 50 out of 170, right? You take the total sample size, it's not the S-nodes. And then confidence interval is the Z critical value, right? Then 0.29 times 0.66 over 170, the sample size. So you got to within 7%. And then you could do a sample size determination. Suppose you wanted to get within 0.03. How many people do you need? And so there's the bound, right? And then this is the one using the information we have, which you would probably do in this case, right? And then this is the critical value. Then you just have to square this, and it comes out to, like I had it wrong, 879. Oh yeah, I had 6 ones, it says 7. If you do it the conservative way, you just put in P, Q equal to 1/2, that's the way to remember it. And then, it comes out to much smaller, right? It comes out to 106 P. No, much larger. 1,068.
Which makes sense because you need a bigger sample size.
Right, right. You're taking the worst case scenario. But if your information is poor, it's probably the best way to go. It's only in a binomial setting where you get this approximation. Any other questions on it? Let's start off with the sign. Oh, you want to look at it?
Yes.
I can't figure it out. It seems to work with the other people. No, the dock cams work, although it's slow. It's the. Yeah. For some reason, I like American. Amazing.
Still. It's like they had a block on this building.
Okay, so, okay, let's talk a little bit, well, let's talk about the problem, then we'll come back and do the. So I hate to. You may not come back, okay? So let's do this again. I think I will. Let's do some make, and then we can do the problem while we have the time, so we can do some of the calculations first. Now, when you go to lab, you want to look for a Minitab 16 icon. Minitabs, I think it's in all labs here. They have a campus-wide license, so there's no problem on the license. Then you just want to click on it. Computer itself. Mini tab is an Excel spreadsheet type thing if you want. And then you can click up here on the menu bar for tools when you're doing that. But you can also use the old-fashioned mini tab with the line commands if you want to. And I have found that useful in class because you can write down the line commands and remember. But we'll operate both ways. Now, the only thing is, you would think that if you clicked on this big wide screen up here, that prompt would come up and to be. Often it doesn't, and we have to set the editor. I think it's under edit. Yeah, command line editor at the very bottom is on. And if you have a blank there, you can click under edit and click on command line editor so it'll come up. You don't have to use it. Many tabs, easy to use, okay. We learn to use it in about 2 minutes. And you can cut and paste right into a Word document with it. And it's nice for downloading data sets right off the web, used with the command line. It's a cinch, and we do a few of those. Okay. So then let's look at the problem again. I still don't want to go away from it, so we'll do a few things. And I was going to look at the, this is exercise 1.0.23, and it has 50 observations, and it scores on a standardized test length, blah, blah, blah. I'm going to use a sign test to test it. They students score better than the school district obtained the P-value. And the median score for the school district is 85, So, we just want to test. Reject. Test is too large, right? And then S is just the number of observations which exceed. If you have some at 85, you just throw them. And then on your cheat sheet, you should have this: expect S to be n over 2, H naught's true, right? I would say the median's 85, so half of the observation should exceed it and half should be less. And the other variance under H naught, and S is n over 2. Which is 10 times a half. And we can do the problem. I've sorted the data, I pre-sorted the data for you. You just need to count up the number over 85. It's easier to count the number less than 85, right? So that's one. There's 15 less. So there's 35 greater, right? So the data come in, S is 35. Is that large enough? P-value is just this, right? And you can use the continuity correction. Now, you could use a binomial table or R whatever, all right? You could do the exact. For class and test, I'm just going to use the Z approximation. So I am going to use the continuity correction. Just back up to cover the rectangle from 34.5 on. And then I just have to standardize it. This would be actually the approximation, like the central limit. And it would be 35. You'd expect 25, right? And the square root of 25 should be 5.
Should be 3.5.
Oh, yeah, right. I'm sorry. Next second. I was trying to do it. That's 90. Still, yeah. So it's 90, it's 2 fifths times 1. Oh, then let's use mini tab. Here we go. You can use mini tab as a calculator. It helps. You have to do that. Tab has constants and columns, and the constants can have matrices too. I'm just going to do the Z score, right? So it's 2 fifths, which is 0.4. Right? This may make you love water. And now I want the p-value, so in R I would do this, right? So it comes out to 3.8. I don't have that in exact. I can click or I can do the command line. The command line would be, this is it. You have to do CDF, K1 and K2. But default is normal 0, 1, and that's all you have to do. K3 be 1 minus K1. Just for a moment, see. It's going to give you the CDF, so it's area to the left, right?
Excuse me. Maximize those resolutions.
Oh, the K3 is. The probability is in K2, I want to let K3. I still did it wrong.
You want 1 minus K2 instead of K1.
Now, probability distributions. Inverse, one kids would be the cumulative probability, standard normal. We'll input a constant. So next one. Our estimate is 50 observations, so it will be, let's see what we have. So we want to go up to 25, 96, right? Median's going to be easy, right? It's going to be, that's the average of these 92 and 96. So you're 11 units above 85. And then for your 95% confidence interval, you need to get that C, right? So again, the rule would be n over 2 minus 1/2 minus 1.96 would be 95% times square root of n over 4. And actually, in some of the calculations we did this, I sort of lost track of it. You see, this would be what, 25 minus 1/2.
Where is that, new river, is that, where is that 5 times coming from?
It's n over square root of n.
And n is 50?
Right, did I calculate that one? Did I correct me? Yeah, I calculated this 24. Well, that changes everything, right? I don't go back and do that. Change that, right? You have to speak up, please. You just go around and just. So it's at least use right here. So the square root of 12. That'll change things. Right? It's 2.5. The square root of 12.5 is definitely 3. We'll probably still do that.
So it's what, 24 and a half?
Let's just do the correct value, this,
Sure.
here I'm gonna round up to 18, right, so, it comes out to 17.5. I've already corrected with the continuity correction, so I just go to the nearest integer. So then my confidence will be this, right? I'll actually want, well, I'll put it down, it'll be 18 plus 1, right? And then 2, and then it'll be 50 minus, let's see which one. I want 19 order observations. 30 seconds. I can remember 87 was the 19th, so it goes from 87 to. And you have to count them backwards. Okay, any questions on that? Any questions on that?
Is that 37 or 32?
32.
Any questions on that? Now, we have a point estimate, and a standard error is nice to have, and we have an estimated standard error. I don't know if we talked about this or not, in general. The estimate on this. Let's get the symmetric confidence interval, and the standard error. And then we bring this parameter in as tau sub s. This is actually the estimate, but we'll talk about what it is in a moment. But the estimate is straightforward, it's just really n times the length of the confidence interval from this computer. Divide by 2 times z squared. Now that's a scale parameter, it's the length of the confidence interval, which I've been referred to. Not too much closer. You can blow it up by again. Okay. So for our example, it would be the square root of 50. And the length of the confidence interval would be 105 minus 87. And down here we would have that 95%. So this length is what? 18 units, right? So it's 18 times the square root of 50. Yeah. That's the scale parameter, 32.46. But then the standard error is nothing more than, you can do cancellation if you want to, it's just not standard error. The standard error then is theta hat. Is tau hat, so that's what it's screwed. So you get rid of the square root of that. So it's 32.46. Well, I didn't put 10. So I'll have to put it's made 10, and I divide it by the square root. So that standard error is 4.59. Then you can do a symmetric interval. And the symmetric interval is just like the ones we've been using. It's the critical value times the standard error. So it would be what, 96? This one is in channel. They took out the garbage cans, and this is what's happening.
I would like
Yeah. You have to bring your own garbage can. So would be that. Oh, pen. So it's 9. That's the root n cancels out. That's why we've got this integer. But anyways, then it would be 96 plus or minus 9. Okay. And the length is the same, it's 18. Right? So we would go from what? 87 to 118.
105.
Yeah. Actually, it agrees on this. It won't always. Any questions on that? So while we're at it, we should do a few more things with Minitab. That why don't we just generate some data? How about the weights of or how about the heights of 25 adult women? Right? Let's see. The average height is about 5'4". We'll get to the same deviation of these things. So, here's our sample. We can just get to a Minitab. And the command is random. And what did I say? Sample size 25, right? Then just put it in C1. Let's do normal heights, right? And then the mean would be 64 inches, right? And standard deviation is 2. Then in C1, have your data. And again, you can click to do that. There's a random generation probably under calculator. So you can do that with that command. Okay? Then you won't have to do this on the screen. But see, on the screen, then you can just write down those two commands, so you know what I did. Okay? Now, why don't we make them look like heights? We would never see it measured to the 1,000th of an inch. So, I'll just round the data and put it in C2. See, now we have round data in C2. And I could just print it. So, there's some data. Okay. Then there's box plots. Just plots. Let's do the box plots if we have any outliers. Single, that's exactly what we want. And then it's like C2, might as well do. You can click that in this too. And then you can put labels on it if you want to set it. There's our box plot. We don't have any outliers. The median looks like it's around 64, which is not shocking. It looks like it's a little bit higher, right? And we can get those statistics now. And then we go through the sign test. But if you want to, if you're on here, you can use the sign test here. I think it's just S test. Okay, now I don't know where to put the null hypotheses in, so what can I do? Suppose I really wanted to test theta equal to 64. Okay, then I could do the sign test, right? But then I have to know where to put the 64 in the command. That's worth remembering, don't we? So I want to test this, right? Let's do a two-sided test. I have to remember that. It's one-sided. Two-sided is always default. I could just come up with new variables this. And then for the y, my test is this. Zero is always default. I could do that if it's let C3 be C2 minus 64. Okay, and then we'll just do a sign test. I think it's S test. You just go default all the way on C3. Sample size is 25, there are 10 below, there are 3 equal, there are 12 above, you're not going to use that H naught. But the two-sided p-value is 0.83. Okay? And I think the yard command for sign test is, I think it's sign.test. If you wanted to do this default, you do the same thing. So do that. You could do one-sided test on think it's all. I think it's all. Let's see, the one that makes sense here, looking at the data. Yes. See, then you're testing variance zero, and the p-value would be about 42. Any questions on that? The sign test is easy to do by hand, right? Because you have a big data set. But if you're working with a machine, you might as well have the machine do it. Yeah, you won't be making dumb errors like I did here. That was a dumb error. It's in 95. This is one thing SPSS doesn't have. Someone told me this, I don't know, you can correct me if I'm wrong, but in SPSS you cannot do one-sided test. How about the five, like this statistical statistics that is described? Okay, the mean, the standard deviation come out, the minimum, Q1, median, Q3, and the max. The last five are discrepancies. And the confidence interval, just do S int, cent. Default's 95%. The problem is it gives you again, you have a trouble with confidence for the binomial. In this case, we just picked the middle one, it would be closest to 95%. In this case, it's 62 to 66. And it also gives you the estimate. The estimate actually is 62. And the sign test is very, very robust. I'll just change the seventh observation. 61, it's 62, right? I'll just change it to 26. This may affect it a bit, and it's really close to the mean. It didn't change the confidence. Okay, so now we have an observation of 26. But the confidence interval is very robust, it didn't change. You wouldn't want the outlier to affect the center, all right? You want a robust statistic as much as possible. Okay, any questions on that or mini tally? Okay, so let's talk about efficiency, but I think first I'll go into the sign rank Wilcox and I want to talk about it, and then we'll go back to efficiency. We'll do efficiency for a while. I mean, we have to say, I mean, why wouldn't you use the sign test? Why am I going to talk about another procedure? And then when we come back to efficiency, we'll see why. Okay, the procedure I want to talk about next is the sign rank Wilcoxon. And the sign rank Wilcoxon does assume symmetry. You know, again, let's look at one side one. And this would be an H0 picture, right? Median, right? Data is still the median. Grammar doesn't change.
Now, the sign test only concentrated on whether it was greater than theta naught or less than theta naught. It's all it looked at. It didn't look at how far it was from theta naught. And you could say, well, it looks like I think you're losing some information there. For instance, if you do a t-test, it will, right? You can write the test statistic as, here's your t-test. That's your t-test. That's a horrible way to write it, but it will come out. It works because if this is positive, then the sign will be 1, okay? The sign is just, it's 1 if it's positive, it's minus 1 if it's negative. So if this is positive, the absolute value would be the value itself, and the sign is 1. And if it's negative, then the absolute value is negative, but this sign is minus 1. So no matter how it comes out, this is your favorite statistic in your, first methods class, right? That's the t-test, right? If I divide this by n, it will be x bar minus theta naught. Okay? So notice the t-test brings in the information. This is the distance from theta naught. So if the measurement is here, this is the distance. If the measurement's here, this is the distance. Also, if the measurement's down here, it's the same distance, you just have a negative. Okay? Someday I'll bring this. See, if the x is here, or if the x is here, these get the same weight in this t-test. They both have this, just look at my sign. Now the sign test just has that. That's a sign test, right? That'll count up the number above theta naught minus the number below theta naught. If none are equal to theta naught, then the addition of those two things I just mentioned is that. You're either above or you're below, okay? So, if I blot out this, okay, that t will be the sign test. It will be the number above. Minus the number below. But if they're not equal to theta naught, then this will add up to n. So I can rewrite this as 2 times the number above. Minus a constant, it won't matter. Okay? It's, so I write down this expression, it is a t-test. If I cover up this absolute value, it's a sign test. I want something in between, so I won't use that distance, that's a t-test. I'll just rank them. I'll rank them from low to high, and that's my sign rank voltage. I'm using T. is low to high. One to 10. And it's on the absolute value. Now, if I do the sign test, it's distribution free. If I do the t-test, it's not. It depends on distribution. And if I do the sign rank Wilcoxon, it's distribution free. In other words, if instead of using a distance, I just use the rank of the distance, I still have distribution freeness. Now, this is cumbersome with that sign in, and we don't have to do that for the sign test. We didn't do that, right? We just looked at that. And we can do the same thing for this sign rank Wilcoxon. That's the one we want to use. And differentiate, I'll call it T plus. It will be the sum of just the positive deviations with the x bigger than theta of the rank of x minus. Now, this involves the distances, and those weights will be the same if the distribution is symmetric. Okay? And so there's a, this is the bad news in this. For theory, we need symmetry. But we could, there's a way we could line this out. Okay. Let's do a good example. This is a good way to say it. I'm reading 1 plus 10. If you do the sign test, it would be a number over 10, but actually it would be 4, right? We're going to do the sign rank Wilcoxon. And then what do we have to do? Well, if you're going to do it by hand, you have the table here. The rows are proceeds.
S here stands for
Sign.
some
Sign.
sign.
The square observations over time. And then how about this one? Well, subtract, you got to subtract off the 10, right? But leave the sign, right? Now do the ranks of the absolute value. And if I do it by hand, I just like to put the ranks below. So here's the smallest ones in absolute value. I have 2 of them, and they'll split the ranks 1 and 2. So this will get rank 1.5, this will get rank 1. Now I've used ranks 1 and 2, I'm on rank 3. In absolute value, this gets rank 3. This gets rank 4, this gets rank 5. So I just, if there were 3 2s, they would split the ranks 1, 2, and 3. The average would be 2. We just take the average of the ranks that we were assigned. But our next rank, those it's like we spend those. Okay? In this case, we spent the ranks 1 and 2. The next one is 3. So then T plus, you would just add up the ones which have positive signs, and you can get this. This is the only one with a negative sign, so you add these ranks. So 13 and 9. Now, how big is too big? Okay, we're going to reject it. T plus is too large. And we can at least get the null value very intuitively. Suppose I have a sample of size n, okay, with no ties in data. And my ranks would be 1 through n, okay? And the average rank would be n plus 1 over 2, right? That's the average of the ranks. Okay? So what's the expected value of t plus? Well, it's the average rank, right? And then, but you only sum up the ranks of the positive items. If base not is true, half the items should be positive and half should be negative. So in your sum, you should have n over 2 items. And that would be the average rank, n times n plus 1 over 2. So that's what I expect t plus to be. Now, what's the range of t plus? Well, all the items could be negative, so it could be 0. One item could be positive, it could be the smallest one. So it could be 1. But it's also the sum of everything, right? All the items could be positive, so it would add up to what? They would all be positive. You would add up 1 through n. And if you think about it, this is the range of plus. It could be 0, 1, 2, all the way up to n times n plus 1 over 2. Now remember, the difficulty we had with the sign test was getting p-values and things. In fact, that's one reason for just going through the approximation. You won't have that difficulty with the sign rank because there's almost like n squared items in the rank. So if we have a sample of size 10, it's like, it would be 10 times 11 over 2 would be 55. So in the binomial table, if you have 10, if n is 10, you'll actually have 11 values in the range of the distribution. For t plus, you'll have 55. Okay, it's denser. It's much denser. Okay, the distribution is long-shaped. The variance is not intuitive. There's no intuition in it. I've never been able to come up with it. It is approximately normal. It's a sum of things. There's a slight dependence in it, but it won't hurt the central limit theorem. The central limit theorem kicks in fact very quickly, much more quickly than sign test. Which now this has the standard one. It's not an example of the last couple of minutes we could do the p-value. In the dumb example, t plus is 13.5. I can put down my mean. N is 5 for the data set. And the mean is 5 times 6 over 4, right? Which is 7.5. So on the upside, okay, I just need to calculate the variance, standard deviation, right? It would be 5 times 6 and 11 over 4.
0.71. So now the Z is going to be this, right? I mean, the p-value will be this. We probably still use the continuity fraction, we should. Although we have a tie. So that's 5.5 over 3.7. Oh, you're going to be over 5%. Could be between, oh, I can do it. It's about 7%. Okay, any questions on the sine regular cost? It is distribution free and, I'll give you a reason next time for using it. Okay. Now, it has an associated, estimate and function symbol, then standard, we'll talk about that next time. We'll do the first name, and then if we have time, we'll do efficiency. Okay. And then we'll have a quiz. And the quiz will be,